Okay, good afternoon, everyone. Let's get started. It is my pleasure to introduce Dr. Kyle Blount. Blount?
Yeah.
Okay, sorry. They are an assistant professor in the School of Integrated Sciences, Sustainability and Public Health. Dr. Blount holds a PhD and Master of Science degree in hydrology from the Colorado School of Mines, as well as a bachelor's degree of science degree in environmental geosciences from Texas A&M University. Dr. Blount research focuses on the ecohydrology and sociohydrology of urban systems, water resource management, urban heat, and equitable environmental management. Dr. Blount has published in leading journals, including Landscape and Urban Planning and Water Resources Research. It has presented at major conferences such as the American Geophysical Union Fall Meeting and the National Academies of Sciences. Moreover, Dr. Blount serves as an associate editor for urban hydrology at the Journal of Hydrology and has been recognized with several awards, including the U.S. Competitive Scholarly Research Grant and the Early Career Scholarship Award at U.S. Another significant accomplishment of Dr. Blount is that they recently received a nearly $400,000 award from the National Science Foundation. And as you know, this kind of grants are highly competitive. So it's a great, a very important recognition of their work. And the project related to the National Science Foundation is to study urban water movement and its effects on ecosystems and public health. Please joining me in welcoming Dr. Blount, who will share their research with us.
I was just in here teaching at 10 and I did not get applause then, so we're already off to a good start. I hope it's okay. I took a little bit of liberty. The reason I was asked to share is because I received that competitive scholarly research grant and talk about the results of that project. And I'm going to do that. But this is also the first presentation in this forum that I have given since I arrived at UIS. This is my third year. And I know that often we feel pretty siloed and don't know what each other are doing. So I'm going to take the opportunity to tell you a little bit about me and my work more broadly than just that project, in addition to talking through that project. And then I also wanted to highlight the work on the CSRG grant that I'm presenting today allowed me to hire a couple of students to work on that project. And they contributed pretty significantly to what you're going to see from that project today. And that's Praise Idowu, who is a BS student in computer science, Carmen Flesh, who is a biology student, and Anwar Azim, who is a master's student in environmental sciences. So with that, I'm going to give you a quick overview of me and my work. In Dr. Vasquez's lovely introduction, she mentioned sociohydrology and ecohydrology. So I have become obnoxiously academic and combined them to say that I do socio-ecohydrology. But if we break that down a little bit, my degrees, my formal training are in hydrology. So thinking about the physical movement of water through the environment. Many hydrologists also do water quality, although that's been a little bit less a part of my work. The ecohydrology part comes in thinking about interactions between plants, ecosystems, and water resources. And then the sociohydrology got tacked on as I started working in urban systems because you can't ignore the people in those places. And so I have decided to just run with this obnoxiously academic term, but break it down and explain it every time I talk about it. So what that looks like in practice, I do some field and lab-based ecohydrology. So the figures here, one of them is from my ecohydrology lab course. For those of you online, I think you can probably see my mouse. This one here, the students in that course looking at water potential from trees. This picture here is from when I was a postdoc looking at evaporation in the lab, and that's related to a public demonstration activity and lab activity that I will talk about. Have some long-term monitoring of environmental conditions at individual plots that I'll talk about a little bit, and then also Dr. Rothfuss is in the room, but we are in that picture installing a weather station at the field station at Lake Springfield, which I will follow up with you about because we still need to finish a couple of things up, and I am delinquent on those. But I also have my current master's student, Ava Maria Mendoza, there who helped us install that. I also do work with remote sensing, environmental modeling, and big data. So that first picture there is Eric Small, who is my first master's student here at UIS. And he worked for IEPA and did a project modeling PFAS in groundwater during his time here at UIS. And then that bottom picture is myself and Praise Idowu in December. I was able to take him with me to the AGU annual meeting in DC this past year to attend that conference, right? And then Praise again. I like to try, to the extent that I am capable, to do some community outreach and engagement. So this is at one of the local STEM fairs in Rochester. But as you probably suspected, most of what we're going to talk about here today is in that kind of remote sensing, modeling, and big data category. And in terms of how I frame my research, I would say my motivation is that water resource management is rapidly changing due to a variety of factors, but largely climate change, growing populations, and new development, as well as redevelopment in cities. And the goal with all of my work is to promote sustainable and resilient urban water systems and then healthy urban communities. On the occasions in which I'm not working in urban systems, that would extend to non-urban populations as well. That has just been the bulk of my recent work. Right? And so I kind of look at that as spanning two different directions. So historically, and I'm not going to talk about it today, but I've looked at the impacts of climate change and wildfires on water supply derived from headwaters catchments. So that's kind of the supply side of urban water systems. And then I also look at water demand in cities, so how water is used after it's treated in a city. And that spans kind of fundamental ecohydrologic processes, so looking at how water moves through the soil, plants, and the air. Okay? And then also, how do we upscale, once we understand those processes at an individual site, how do we scale that up to look at what's happening across neighborhoods, across cities at a bigger scale? And today, mostly talking about that upscaling piece. So to do this, I thought it would be worth talking about a little bit of my previous work and the questions that got me to this project. So during my PhD in Colorado, I looked specifically into outdoor water use in Denver. So I developed a remote sensing algorithm that looked at greenness in different end members, so impervious surfaces, right? That's anything that's paved, okay? Non-irrigated landscapes, so largely open space parks in Denver, and then irrigated landscapes, so that's mostly public parks and golf courses in Denver. And from that, I was able to calculate an estimated irrigation rate for every single census block group in the city and county of Denver. And some of the big takeaways from that is that Denver Water, as a public water utility, has seen their per capita water use decline over the past 20 years, pretty significantly. That is a statistically significant trend over that time. And that's really associated with indoor conservation, right? So installing low flow toilets, low flow shower heads, improvements like that have reduced individual water use in Denver. And what we found is that there is an increasing trend in outdoor water use, although that trend by itself is not statistically significant. But because indoor water use is decreasing, the percentage of water that's used outdoors in Denver is increasing significantly. So as a management priority, that outdoor water use is an increasingly important part of urban water systems to understand and try to reduce that demand. Right? That's also in the context of increasing water reuse. And Denver is really one of the leaders in that. They take wastewater, treat it back to primary drinking water standards. And right now, they send it out mostly to grow operations for marijuana. That's one of the few industries that will take treated wastewater. But as regulations change, I would expect that to go back into additional parts of the system. Right. So that indoor water use, even as it's being reduced, can also be reclaimed, retreated, and reused in not entirely a closed loop system, but something akin to that. Okay? Whereas the outdoor water use that you put on your lawn outside just goes away, right? Not really goes away, but it doesn't go back to the system, right? So that's a really important management target. The other piece of this that was really important, if we look at the plot at the bottom here, there is no relationship between precipitation in any given year and how much irrigation was applied to Denver landscapes. However, there is a significant relationship with daily maximum temperature, basically how hot it's getting during the summer. Some of that is probably phenology related. People like green lawns. They turn on the irrigation systems, right? And they likely don't adjust them at all unless things start getting brown. That happens when it gets hotter and drier, right? So in those hotter years, we might see increases in water use. But they don't usually turn it off or decrease the watering when it's cooler or when it's wetter. Right? So largely related to human behavior as well. But what that means is almost all of the significant trends for block groups in Denver, where there was a significantly increasing trend in outdoor water use or irrigation outdoors, was explained by interannual variation and significantly increasing temperatures in those locations. So another important piece of what's happening in Denver is called infill development. This is happening a lot of other places, but it's this idea of redeveloping what are considered underutilized parcels. So they're parcels of land in a city that are not perhaps used to their maximum value. It kind of comes from an urban planning and economic perspective, but there are a lot of environmental benefits to more dense development in cities. And so what that really looks like in Denver and in most places in the US is converting single family residential properties to multifamily residential properties. And so I love this picture. This is from Denver. We have this single family home right in the middle, traditional smaller home, front and backyard. And on either side, we have these big either condos or apartment complexes that take up the entire parcel with absolutely no green space outside. Right? And so that's the transition, is moving from those single family into the multifamily residences, right? Which changes the landscape and the composition and organization of green space in cities. And so I really wanted to understand what was happening through that redevelopment. So this other piece of that project looked at every single individual parcel, its current land use, and then within this Berkeley neighborhood that's in Northwest Denver, took all of the single family properties and evaluated scenarios for low levels of redevelopment, which is about 10% of the parcels being redeveloped, moderate redevelopment, and high redevelopment. Okay. And through that study, what we saw was not only from the previous one did we have an understanding of the impact of climate on irrigation in urban spaces, but we could understand how land use and zoning changes might influence that outdoor water use. So parks and open space, unsurprisingly, have the highest irrigation rates. Commercial and industrial properties, which often don't have any green space at all, have the lowest. But there is a lot higher irrigation rate for these single family properties, which is the SFR on that top graph, than the multifamily, which is the MFR to its left. Okay. And when we redeveloped virtually redeveloped these properties, outdoor water use did decrease significantly. And it's actually pretty significant savings, depending on how much redevelopment happens across the city and county of Denver, could really reduce the total water demands for Denver water in those locations. Okay. But I say that because we start pulling out the impacts of land use change, climate change on irrigation. But these are virtually redeveloped. It's not physics-based modeling, and you see a really straight linear trend, right? And that's a product of how we chose to basically virtually resample. That trend is almost certainly not linear. There are probably decreasing trends or decreasing returns as development gets more dense. And so finishing my PhD with this project, I really wanted to look at what are some of the interactions between heat and water, because as you increase that density in urban systems, you reduce the amount of green space left, but you also increase the urban heat islands. Right? If it's hotter, we know that there should be a greater demand for irrigation in the remaining green spaces, right? So there should be some type of diminishing returns in that system. So with that, taking a step back, some theoretical grounding here. Looking at both water and energy balances. Okay, I'm sorry this gets a little technical, but it's really important to understand a lot of this work. So from a water balance perspective at the landscape, we want to look at everything coming into the landscape and everything leaving the landscape. So we have that gray arrow P coming in, that's precipitation, all the precipitation that falls on our landscape. And then that precipitation that falls can go one of basically three places. And this is a little simplified, but conceptually valid, right? So that ET arrow is evapotranspiration. So it's all of the water that evaporates plus all of the water that transpires through plants and goes back into the atmosphere. We have that orange Q arrow, which is runoff. Okay, that's all the water that runs off the surface, and this would, in theory, be into a stream, right, or maybe a sewer system. We have that R, which is deep drainage, so that's infiltration, so water that goes down and becomes a part of groundwater. And we have a change in storage component because depending on the time that you're looking at, soil water can change through time as well. From an energy balance perspective, we're doing the same thing. We're looking at all of the incoming components and all of the outgoing components. Okay? So if you think about the electromagnetic spectrum, which includes visible light, right? We have infrared light. What's relevant physiologically is both the shortwave and longwave radiation. Right? So from the sun, we have both shortwave and longwave radiation coming in and hitting the surface. Okay? Based on characteristics of the land surface, some of that reflects back off of the surface without ever being absorbed. So that's the SW out and the LW out being re-radiated back into the atmosphere. Okay, but what is absorbed and stays at the surface, again, a little oversimplified, but goes one of three places primarily. G is the ground heat flux, so that's what actually warms up the ground and the soil beneath the surface. Okay. That H sub S is sensible heat, so that is what radiates back as heat and warms the air. Right? So if you think about walking across a parking lot on a hot summer day and you feel that heat as you step onto the concrete, that's that sensible heat coming off of the pavement. Okay. And the other place that it can go is latent heat flux, which is the same as ET. Right? We use ET from water balance perspective. We use latent heat flux from an energy balance perspective, but those are essentially the same thing. Right? They're directly linked, and they're both ways to account for how much water is being evaporated from the land surface and going back into the atmosphere. Because of the latent heat of vaporization of water, if we know how much energy is used to evaporate water, we know how much water was evaporated. Right? That's a constant. So in that way, those are essentially the same concepts here. They're directly linked. And so what this means in cities is there's this trade-off between latent heat and sensible heat. So the green and red arrows in the center image, okay, which based on the actual land cover that's there, that energy that comes in can either go to evaporate water or it's going to go to heat up the land surface. So because of that trade-off, this change in land cover, change in green space composition of urban systems has a direct effect to energy, and that is a part of what creates the urban heat island effect that we'll talk about in a minute. So I mentioned I was curious. That relationship is probably nonlinear. There are feedbacks that we're not accounting for in that very simplistic model. Okay, so how are we going to do that? I had the opportunity to begin to answer that question in my postdoc. So I did that in Washington State, Southwest Washington, just across the river from Portland, Oregon, on the Washington State University of Vancouver campus. And we have sites set up there that look like the picture on the right. Okay, so we have a bunch of different highly instrumented plots where we are measuring things from below the surface to above the surface and trying to understand the full water and energy balance that I showed you before. So all of those arrows, we're trying to quantify all of those arrows for each of these plots. Okay. And we have them split up, varied between hot sites that are located next to a parking lot and cool sites that are located in a riparian area further away from most of the built up area on campus. And it is, there is a pretty significant difference during the summer in how hot those are. The hot site is about 10 degrees warmer. So in that way, despite the fact that this is a kind of peri-urban area, we can simulate what's happening in urban areas at that hot site and compare it to what's happening in rural areas at that cool site. So kind of two end members there. And just because I think people like the visualization to see what's happening at each of these plots and what data we're collecting. Hey, we're collecting incoming radiation. We're collecting meteorological data above the surface. We're collecting surface temperature. And then below each of the surfaces, we have soil moisture and temperature sensors. So that we can basically measure when water hits each of these surfaces, where does it go, above and below ground? And when energy comes in from solar radiation to each of these plots, where does it go? Up and down. Okay. And I didn't show pictures of this, but we have plots that are below trees. We have plots that have grass, plots that are mulched, and then we have plots that have this asphalt covering. Okay, so we can also look at the impact of different urban land covers across these. All right, so previous work, backgrounds. I'll talk a little bit about the motivation for this project. Okay, again, I know this is a lot, but I want to make sure we're all on the same page, and I feel like it's more useful for you to get to know who I am and what I do than just the results of one particular project alone. So I talked about this, urban heat islands. You might have seen this figure before, but cities are hotter than surrounding rural areas. Okay, on average, that's anywhere from like 2 to 5 degrees warmer, but that can be over 20 degrees Fahrenheit warmer during the evenings. So pretty drastic changes between really dense urban centers and surrounding rural areas. Okay. And the creation of urban heat islands is associated with low albedo materials. So when I talked about the incoming solar radiation and we had some going out, right, that's controlled by the albedo of each land surface. And the albedo is just the ratio of, the amount of light or energy that's reflected versus how much is coming in. So a high albedo surface would be something that's white or lighter in color. It's going to have a higher albedo. That means more of that incoming energy is going to be reflected back out. Okay. Whereas a low albedo material, something like a dark pavement, asphalt, is going to absorb a lot more of that energy. It's going to have a low albedo. And that contributes to urban heat islands. Increased thermal mass, so when you build buildings up out of these materials like concrete that can absorb and retain energy that contributes to intensification. We also have reduced shading and evapotranspiration. Right? I already talked about the energy balance. It can either go to sensible heat or latent heat. It can either go to evaporating water or it can go to heating up the environment. if you have less water, less soil, fewer plants, less of that energy can go to evapotranspiration, more of it has to go to heating up the surrounding environment. And then we also have human activities, industrial processes that generate heat. Think about power plants. They put off a lot of heat into the environment, and that contributes as well. That has a lot of impacts on urban residents and the systems, right? So there are a large number of impacts to human health, directly heat exhaustion and heat stroke, especially during extreme heat events. Okay. It worsens air and water quality. Okay. It can aggravate pre-existing conditions. So people who have things like asthma are more affected by extreme heat. Can decrease the ability to do outdoor work and recreation. One that I find really interesting is that extreme heat worsens mental health and is associated with increased rates of interpersonal violence. So higher violent crime rates, whereas when and where it's hotter. Extreme heat is the leading weather-related cause of death in the US. Okay? And the US is not even the place where these things are worse. If you think about places like India, extreme heat events are of really immediate concern. Also has impacts on agriculture and ecosystems, so reducing production, stressing anything that lives in the same way that humans are stressed by these conditions. Animals are stressed by the conditions. And what I saw a lot when I lived through the most severe heat wave the Pacific Northwest has ever had while I was up there, a lot of trees scorching. So after these heat waves, you'll go out and a lot of the trees either are entirely dead or it has scorched the ends of the trees. And then there are impacts on infrastructure. So one of the most dramatic ones is that it will get hot enough to literally bend rail lines that then have to be repaired. So there's a picture of that there. And then, of course, increased energy demands associated with increased temperatures for AC use as well, which can stress already stressed electrical grids, especially in certain locations in the country. It's also motivated by the fact that there are equity considerations surrounding heat in urban areas. So this is a figure from a paper looking at the distribution of evening heat in Portland. Okay. Anywhere where it's red is hotter, blue is cooler. Probably intuitive for you, right? But there are industrial areas near transportation lanes that are much, much warmer. So this heat, even though the whole urban heat islands happens and affects the entire city, local iterations of urban heat are not spread out evenly within cities. And unsurprisingly, these impacts are most severe in communities that are primarily Black, Latino, or Indigenous. Okay? So a large, over half of both Black and Hispanic populations live in areas where they are likely to be exposed to extreme heat and heat waves and excessive heat. And cannot get out of here without acknowledging the history of housing policy, things like redlining that have resulted in residential segregation in most cities, and then the associated disinvestment from areas that are primarily minoritized communities over decades, which means that they are less green, they are more hot, and they are more dangerous to live in from an environmental perspective. So with all that in mind, I'm going to talk about the CSRG, the Competitive Scholarly Research Grant, looking at the impacts of urban configuration and heat on heat and water transfer using a model called InViewMet. So I promise this is the wordiest slide. I just did not have the brain energy to think about how to reduce this. So I'm sorry for that. I try not to do this. But the objectives from that proposal were to use InViewMet to explore how the model structure and parameters affect the outputs and identify best practices and limitations for using this model for heat and water transfer in the environment. Okay? This model is used by urban planners and architects a lot to think about things like building energy use, outdoor thermal comfort in courtyards when they're designing buildings as well. But it really hasn't been used as extensively, although it's starting to pop up a lot more in the last couple of years in academic research. It's also proprietary software owned by now a new company, but it's a private company, and so it isn't open source. A lot of people can't necessarily use it, and although it has the capability to model all of these things that I'm interested in, it wasn't exactly designed to do that. So I wanted to evaluate how appropriate it was for that purpose. And then I also wanted to think about redevelopment scenarios. So I showed you that slide of infill development, moving from single family properties to multifamily properties. So trying to get a better understanding of what that transition in a residential neighborhood would do to water demand, transpiration from remaining green spaces, and heat generation at a local scale. Okay. I will go ahead and prime you that this is not finished, despite the fact that the funding is up. And we'll talk about a couple of reasons for that in a minute. But ideally, and hopefully what the final output will be comparing these processes across 10 different cities in various climates across the US. Right? So we have a little bit of an understanding of how these processes might vary in different climates. So to give you a little bit of information about the EnviMet model itself, some of you will glaze over on this slide, and that is totally fine. If you get that it's an urban microclimate model, you're good. Okay. But for those of you who know and are potentially interested in the details, it is a computational fluid dynamics model, and it uses Reynolds average Navier-Stokes equations. So those are kind of standard for fluid dynamics computational models. It solves for atmospheric flow and heat transfer in these urban settings. Okay. And it's really two different models. Okay. The model example that you see here is the 3D model that includes atmospheric variables, soil, and vegetation, as well as the built environment. And then there's also a 1D atmospheric boundary model that's used as forcing data. They're used to force with forcing data and run the model. And it has dynamic coupling of the atmosphere with soil and vegetation moisture processes, which is one of the reasons that we can look at how water moves through urban landscapes with this model, is because it does dynamically update soil moisture, transpiration, humidity. So we can kind of look at how water is moving between the soil, plants, and atmosphere. So looking at objective 1, and this is one that during the project Praise Adowu largely tackled. And this is actually a model created from campus here at UIS. So he took a small area of campus and digitized it and turned it into this model that you see on the right as a representation to be able to run this. And remember that objective 1 is to understand how well the model functions, right, across these different objectives. So the example results that I'm going to show you today are specifically just looking at vertical grid resolution. Right? So this is a 3-dimensional model, and you can think about that 3-dimensional space as being occupied by cubes, right? And you get to choose how big those cubes are, right, in all 3 directions. So one of the most important variables, though, is that vertical grid resolution. So how tall are each of those individual grids that you stack on top of each other to create the model domain? Okay. And so the results here are going to show comparisons of outputs with a 0.5 meter, meter, and 2 meter vertical resolution. We're going to look at results. There are a lot more output results that we can look at, but highlight air temperature and PET, which is physiological equivalent temperature. So that's actually what you would feel if you were in that location, right? You don't necessarily feel the air temperature, humidity, whether you're in the sun or the shade. All of those things affect how hot you perceive it to be. So PET is more about how hot it feels than how hot it actually is. Okay. And all of these results are pulling from a 1.25 meter height, which is about pedestrian height, on a hot summer day at 4 p.m. And so each of these, and I'm sorry, did not have time to go back and fix the symbols and display for these. In that you see a divergent color scheme here, and you think hot, cold, increase, decrease. But the center point is not 0. So you can't interpret the colors quite that way. So I need to go back and fix this. But this is that model domain, and what this is doing is comparing at that 1.25 meter height, what is the difference in temperature output when we have the half-meter height versus the 1 meter height. Okay. And so what you can see is that it does vary some across the model domain. Okay. Generally speaking, if you look at this, kind of the middle blue is about 0, no change. So everything that's light blue and brown is hotter, which means that the 1 meter resolution model produced results that were hotter than the half-meter resolution results. Okay, so across most of the model domain, it was hotter when we increased that vertical resolution. Okay. But you also see kind of the effects of how that vertical resolution handles what's happening in aerodynamics around the buildings. Okay. So the wind direction here is from west to east or left to right directly across the model. So this big brown patch behind each of the buildings indicates that right behind a building, the way that the model is handling the aerodynamics as wind blows around that building is really greatly impacted by that vertical grid resolution. Okay. And that is an issue because conceptually what the model is representing shouldn't change based on the scale that you're examining it at, right? And so in the modeling world, we call this model convergence, which is that regardless of the grid size, you should get the same output results. If you're getting different results, that means the model is not accurately resolving the processes that you're trying to model. Okay. So that is one concern. When we look at air temperature differences between the 1 and 2 meter, okay, we see similar things, right? We have some differences in how the model is representing these processes, and it's giving us different outputs. Excuse me. This time, 0 is off the scale, so everything here is negative, right? Which means the 1 meter is less hot than the 2 meter. So half meter is less hot than 1 meter. 1 meter is less hot than 2 meter. So there's a systemic increase in temperature at this height as you increase that vertical grid resolution. So again, that is an issue that needs to be resolved. One of the goals of this project is to develop best practices for using NVMet for these applications. And so we need to, I don't know with the data that we have that we're going to be able to do that the way that I envisioned it, because we don't have data to validate which of these is most accurate. Okay? But we do need to carefully think about how that vertical resolution impacts the output results and what that looks like. Okay. When we look at PET, or that physiologically equivalent temperature, okay, we see similar differences. Although this one thankfully is a little bit smaller, that kind of light brown is right around 0. So a lot of this is pretty similar between the two models, but we still see that downwind effect as of the aerodynamic resolution in the model on downwind of the wind direction on each of these buildings. Okay. When we compare 1 and 2 meter grid resolutions, we actually see a little bit more difference. So 0 here is kind of that darker brown. Most of the blues here mean that it is estimating that we would feel cooler with the 2 meter resolution than the 1 meter resolution. So again, all of this is to say and underscore there are issues with model convergence. NVMet, the software, and now open source, I think, is who just bought them about 6 months ago. They have no formal guidance on this. Okay, the only guidance they give you for setting up your models is that the top of the model domain needs to be twice as high as the tallest building in your domain. Okay, but for all of these other parameters, they provide no guidance, which means that if you're not doing this kind of sensitivity analysis to see how changing these parameters affects your outputs, you may just run one version of the models, think that that's a good output, and have no clue that it's not accurately representing the processes that you're trying to understand. So objective 2, that redevelopment and climate, is one that's really ongoing. Okay. The goal here was to evaluate summer heat wave days, and those are defined as greater than the 95th percentile high temperature in each city, because again, there will be 10 different cities in this study, looking at both pre and post redevelopment scenarios. And this is what those redevelopment scenarios look like. So on the left, we have a bunch of single family homes. It's very Stepford wise when you look at it in this way. Everything is all nice and uniform. But thinking about residential areas of cities, moving from all single family homes, which is kind of the traditional suburban development pattern, into some of these mixed use. And so you can see a little harder, but the ones that take up more of the property and are a little bit taller on the right are those infill development properties. So when we change a certain number of properties in each of these models from that single family to multifamily residential, what does that do to our outputs? How does it affect how hot it gets? And what does it do to the movement of water in the remaining green space? So that work is ongoing. I mentioned the software and the company that owns it just got bought out in November. Shortly thereafter, they released this new version 5.7 of the model, which has a bunch of updates. And so with the release of this new model and me not getting these results out prior to its release, it's really not all that relevant to look at the older versions of the models. So what I have to do is go back and redo all of the analyses in the newer version of the model to be able to publish and share those. So that work is ongoing. And as I'm sure all of you know, the ability to get research done during the semester is virtually non-existent. So that is somewhat of a summer project to hopefully wrap up and finish for me. But to kind of highlight some of the progress on this project specifically, preliminary takeaways, there are model convergence issues that persist. And so there is this real need for additional guidance. It does not necessarily have to come from me, but if the company itself is not going to produce it, I will try to take the time to do it myself on best practices, on what model parameterizations are going to most accurately represent the model domains that we're trying to understand, right? And then that ongoing work, redoing all these simulations in the new updated version of the software, putting together some of those best practices, and then looking at the differences and completing objective 2 between those different cities and the redevelopment scenario. And so, yeah, I'm still decent on time. Just a couple of highlights I kind of started broad, zoomed into the project. I'm going to broaden it back out again here. Just thinking about extending the themes from this project and from the work that I've talked about into things that are continuing and other types of activity. So one of the things that I've been thinking about a lot is how best to integrate teaching, research, and outreach. We're all very busy. And so if we can combine these things into similar activities, that is a great way to be efficient and do some of these simultaneously. So on these themes and thinking about differences in heat and water balances across different urban land surfaces, I've got some images here from a project that started while I was a postdoc. Did a science communication fellowship with the Oregon Museum of Science and Industry in Portland. And as a part of that, we developed a public display and then had the opportunity to offer this public display during various events that the museum, OMSI, would host. And so what we ended up doing is creating this display with these different land covers. So they're just little tubes that have different land covers in them. You see the grass, there's mulch, we have bare soil, asphalt, and then some pebbles, right? Just different things that you might find in an urban environment. We have multiples of them because one of them is dry, one of them is wet. So we fill the rest of that surface up with water so that there's a constant supply of water. So how do these processes vary when it's wet versus dry? And we're really getting at that split in energy balance between latent heat, or ET, and sensible heat. Right? How hot does it get when it's dry versus when it's wet? Where is that energy going? Going to evaporate water, right? And then above that is what the setup looks like. So we had a heat lamp. We would put these underneath the heat lamp, and then we had this very nice, it is like $25,000 thermal camera that I don't have here at UIS anymore. Maybe one day I'll get enough money to buy one. But we had it set up and hooked up to a monitor so that they could see live how the temperatures varied across those. Okay. And then that third set, really cool. The middle picture is Garrett, who was also a postdoc in the same lab that I was in. And you'll see a spray bottle there, and that has ethanol in it. Ethanol has a much lower latent heat of vaporization, which just means it evaporates faster. And so live on that computer screen, you can spray the dry surface, watch that temperature go down, and then within a couple of seconds, it's back up to what it was before. So you can kind of, in real time, see that cooling effect and then the evaporation and heating up of the land surface. And that picture is from one of the events with OMSI. But what I don't have the $25,000 camera, but I do have this really cool thermal camera that plugs into your cell phone if you have the app. And so I get to use this in my lab. And we do this actually as a lab as well in my ecohydrology class. So it's a public demonstration. And that's more quantitative, kind of look at these, compare, think about what different land cover choices mean for how hot your yard gets at home. And if you're a homeowner, what choices might you want to make if you don't want it to be too hot? Questions like that. The paper that's up here is just explaining the actual quantitative activity where we measure both a water balance and an energy balance approach to the amount of water that is evaporated during the course of a laboratory exercise. So it is a quantitative calculation of evapotranspiration that I do in my ecohydrology lab. But I get to use the camera the phone thermal camera to kind of show that as well while we're there. And usually do a heat tour where we just walk around and see what in the environment is hot and cool while we're waiting on the land surfaces to heat up. And then I also want to highlight a couple of ongoing things, mainly because I know there are other faculty who may have overlapping or similar interests, and I'm always open to collaborations when I have the capacity to do so. So I have several other projects in different iterations of asking these same questions about heat and water in cities on urban microclimate, that heat water transfer and redevelopment. I have a master's student, she was in one of the pictures earlier, Ava Maria, is working on understanding kind of watershed biogeochemical processes and how they affect cyanobacteria growth in Lake Springfield. The grant that Dr. Vasquez mentioned earlier that was just funded for the next 4.5 years from NSF is on the particular role of irrigation water limitations in ecohydrology. My last slide, the next one, is on that. I promise we're almost finished. Currently working on another proposal looking at the impacts of climate, network structure, and human activities on solute mobilization. So actually moving into the water quality world a little bit with some colleagues at the University of Florida. And I'm really excited about that because one of the areas long-term that I thought I might want to look into as well is thinking about stormwater. And you really have to think about water quality there as much as the water quantity. And so as many of you know, to get funding, you have to prove that you know what you're doing. And so having a history of research that involves some water quality will be helpful to that in the future. And I have a meeting with her later today, so we will see. But I have a potential visiting scholar who's a PhD student in Mexico, planning to come and spend the fall here at UIS with me, looking at sociohydrology dynamics. And I intend to have a conversation about whether she really wants to come to the US right now, because it's like we can work from a distance if we need to. But that is potentially coming up as well. So just to highlight that funding that I just got. The title of the project is Evaluating Scale-Dependent Impacts of Irrigation on Water Limitations and Ecohydrologic Functioning of Urban Landscapes. Okay, and this figure is from that, and it's kind of positioning the literature gap, or really the understanding that motivates the work. We have kind of traditional engineering studies that look at runoff and discharge, kind of wastewater treatment and water use. Okay, and then we have kind of natural science studies that look more at interception, soil moisture, ET, plant ecophysiology, and some of that green water cycle. And traditionally, there's been a lot of research on stormwater management, which is kind of a transfer of rainwater back into an engineered system. But there's been much less work on what I spend a lot of my time thinking about, which is irrigation or outdoor water use as a unique transfer of water from those engineered systems back into the environment, and how irrigation support of urban landscapes affects the hydrologic functioning of those landscapes. So how places like public parks in cities function differently because they are irrigated in many places, not universally. So there are a couple of objectives. The first is understanding the irrigation's impact on soil and plant water in urban green space. Okay. Do that with field studies. We have the site at the field station. I'm going to install a site hopefully this summer in conjunction with CWLP here in Springfield. I'm going to use data from the sites in Portland that already exist. Nice benefit of collaborations. And I'm also in partnership with Denver Water going to be installing a site in Denver as well. Then I want to think about upscaling those processes from that like plot scale installation up to what's happening across the landscapes, and do that with some remote sensing analyses. And then trying to think about what happens when we turn that water off, right? So we want to understand how the irrigation support of vegetation in urban green space affects the ecohydrology or the water movement in those spaces. But we often have policy imposed water restrictions, often when it's already hot and dry during drought, right? And so what happens to those landscapes and their cooling capacity, right? There's been one NVMET study done in Europe that showed that after all the soil moisture dried out in a park, the soils in the park were just as hot as the surrounding pavement, right? So we think about urban green spaces as a big solution to urban heat islands, and the shading can definitely still help if we have trees and other shading structures. But because of that split in the energy balance between the latent heat and the sensible heat, if we don't have any more water to evaporate, no more of that energy can go there. And so if we turn off that irrigation, we lose all of that cooling benefit, or at least most of it. So I've talked long enough. I think I have a few minutes for questions, but thank you.
Yeah, so this is a very interesting study. So thank you for mentioning the Navier-Stokes equation, actually. So yeah, that's computation equation. So my question would be the data points you collect at the UIS campus.
Mhm.
Is that green dot, is that the data points?
No, so that's actually where trees are in the
Trees.
model.
Okay.
And we don't have any observational data. So that's something I'd like to do. I submitted a grant this past year to Illinois Water Resource Center that I just found out wasn't funded, which is okay. I have enough to do. But I have a colleague at UIUC, and they have kind of a tiny home village in Champaign to support the on-house population. And because it's funded, there's the opportunity to potentially instrument that. So you actually kind of need air temperature, wind speed, humidity at a pretty well-distributed grid within your study area to be able to actually calibrate and validate the model. And so I'm going to pitch to her. I haven't talked to her about this yet, but I was going to pitch to her to see if she wanted to apply for that funding to see if we couldn't get the instrumentation to collect data in that environment to have better parameterization. Because you're right, without those data, we can see how the model outputs vary, but we don't know which of those is most accurate.
Okay. So the very data is coming from the NVMET, right?
Yeah. So you can either put in generalized climate data for that 1D atmospheric boundary model, Or it has a built-in system where you just tell it what the high temperature is, what the low temperature is, and it will distribute that throughout the day for the simulations based on the location. You tell it where it is, so it has the solar zenith and azimuth, all of that built into the model.
Looks like there are a couple of, I'm sorry. Yeah, same thing. I
Uh,
just noticed
couple of
the
questions
question
in the
online.
chat, yeah.
Is-
Question: what can everyday folks, citizen scientists, do to help water conservation and urban heat issues? Great question. Thanks, Isabel. I think one of them is think about what choices you have to make. So I think one level is if you are a property owner or even renting and have some control over what happens outside, think about, especially here in Illinois, we're not really that water limited, right? So we're not worried too much about having to irrigate a lot of that green space. So, think about what decisions you can make to remove some of that impervious surface, which also has stormwater management benefits. And will also keep at least your local environment cooler. But I think the bigger things are advocating for policy changes. So Isabel, you and I might talk about this a little bit offline because I don't want to talk way past the end of the seminar. But when we do more dense urban development, that's good for a lot of things. It reduces transportation costs and emissions. Mixed land use, more dense residential communities are by and large a good thing, right? They're just a little hotter. And so a lot of communities are trying to replace kind of the private green space associated with, front and back yards for individual single family homes with more collective green space. So public green space, public parks. So having kind of mixed use spaces built around green areas and interspersed with green areas, that will definitely, so advocating for those types of changes, which maybe Springfield is less motivated to redevelop certain areas, but advocating for the inclusion of green space is a good thing. And those public green spaces are also gathering places, right? It's more equitable in terms of access to green space. They promote, better exercise, improved mental health, and better community connections because you see your neighbors and you get to know your neighbors when you're out enjoying the green space. So I think advocating for those policy changes is probably the biggest and most impactful thing that I'd say.
Thank you, Kyle. It's a great talk. Yeah, I do have one question regarding your early work in Denver. You mentioned the indoors water use decline and the outdoor actually increase. Can you explain a little bit what's the main reasons the indoor, per capita water use decline?
Yeah, so I mean, part of that is just physically the installation. So Denver Water had a rebate program for the installation of low flow appliances. So low flow shower heads, low flow toilets. You could basically get reimbursed if you were willing to change out what you had in your house for a more efficient model, which most people are really excited to do. New toilet for free. That's great. So that's associated with a lot. There was also kind of late 90s, this realization that as a drier climate, Denver was not going to have infinite water resources. And so I have never been anywhere that is aware of water use as Denver in terms of a public awareness. And Denver Water has been pretty instrumental in trying to raise public awareness of conservation behaviors. And so I think that general awareness contributes there to the indoor water use as well. One of the things that they're trying to do now that's been done very successfully in other places have a turf grass replacement program. So rebates for replacing your irrigated turf grass with literally anything else, although they won't pay you for AstroTurf because of microplastics. And my friend who works there, everybody's like, just AstroTurf it, and visibly frustrated when people say that. She's like, no, that's not better. But any kind of native plantings or xeriscaping, they have a rebate program. And actually, both Phoenix and Las Vegas have done that very successfully and really significantly reduced their outdoor water use. But from a heat perspective, I would advocate for trying to include some native plantings because they may not transpire as much, and so they may not have quite as much of a cooling benefit, but it's still better than a rock garden in terms of heat.
Kyle, I really appreciated the background on your context on your broader body of work. So I wonder if you could talk a little bit more about your enviable inclusion of students in the research. So what kinds of things you had them doing and maybe what you learned about how to do that well and what some of the challenges were, especially since the software updated and et cetera.
Yeah, I think biggest thing is preservation of data. I think I saw Praise hop on my call, so hi Praise, and thank you for doing a really good job with this. Not that others didn't, but Praise was a little bit more proactive about this in terms of saving the model output files, organizing them by simulation, and so it's pretty easy for me to go back in and find all of what Praise did. He also had the benefit, I have a workstation here on campus. I think the others were working on personal laptops. They had downloaded a free version of the software, so understandably not as directly organized. But I think having a better data management plan, put it in NSF terms going in, is something that I would do. I did have to train everybody, so all the students were working with the model. So the way that I did that was we had a group meeting one week where we went through using the model from start to finish, how to create all of the input files, how to run the simulations, how to look at and examine the output files. And thankfully I recorded that on Zoom, so I won't have to do that personally. I can just share the link with students in the future, so hopefully that'll be efficient. And then I actually put together a step-by-step guide in Word and just went through and did it myself, so they had access to that for support as well.
Company should pay you.
Yeah, well, I haven't shared that with anybody. If they want that, they're gonna have to pay for it. But I think some of the challenge is a time span. There's a lot of training that goes into this. And there's, we have some fantastic students, and Grace, Carmen, and Anwar are excellent students. And so, their ability to pick up and read literature and help summarize literature is already pretty high, especially for the undergrads on the project. But it's just hard to get students up to speed on that. So yeah, I don't know that I have suggestions, but I think that was a challenge. So if anyone here or online has suggestions for how to do that, I'm very open to them. And then, yeah, I think having those check-ins, having the model outputs, and time, putting these model domains together takes a long time, which is part of why I haven't finished doing the updates, is because I wanted to change a couple of things in the model domains, and it's a very lengthy process. I could easily spend an entire week just putting together the model domains before even starting to run any simulations. So that's kind of unique to this model. But yeah, I mean, I think having good students and our students like us have a million different demands on their time, and so sometimes even just the attention and the consistency is a challenge, even when they're paid and they're working their paid hours. But yeah, I think it was great to do. I think on a practical level, if I had it to do over again, I might hire fewer students, but keep them around for longer, so there's a little more continuity. Be helpful. But unless they're just an outstanding student, I wouldn't want to stick them into this alone without peer support. So, I don't know. That was me and your reflections, but.
And thank you for including all of our students.
Okay, there's one question in the chat. I'll answer that before I shut up. I know we're over time. From a municipal standpoint, we have credits on stormwater utility fees for things like adding pervious surfaces. Oh, yeah, sorry. That is Shannon, who's in my GIS class this semester. So thank you, Shannon. Yeah, a lot of places will add stormwater credits. Denver has done this to a certain degree. I'm guessing this is for Champaign, because I know that's where Shannon works. But yeah, a lot of places can add. A lot of places have added like a stormwater tax to your property tax. It's based on how much impervious surface you have on your property. And so that either gets removed, or if you're not adding a tax, that's obviously not something people love. You can offer a tax credit for reducing the amount of impervious surfaces on your individual property. Oh, cool. Yep. Thanks, Shannon. Anything else from people in the room? I don't want to hold people hostage. I'm happy to stick around and talk if anybody wants to, but otherwise, thank you very much.